Hello class, it is Tuesday, April 14th. Today we're going to be looking at confidence intervals, which is a type of measurement for population values. Before I do that, I just want to let you know that your test 3 is graded. The grades are posted on Canvas. The solutions to the test are posted under announcements. So please check out the solutions to that. Make sure you learn from your mistakes so you can prepare yourself to do better on anything that maybe you didn't do well on. For the final exam, that's going to be coming up in a matter of weeks. For the rest of the semester, we have, remember, one more test remaining and then the final exam. Still, as of now, I have no information about how the final exam will be conducted. Chances are I'll probably just make up the exam myself since the test will no longer, of course, be an in-class exam. So we probably have one or two more homeworks remaining and maybe one more lab at this point. I don't want to overwhelm you too much at this point because I know we're probably all getting tired and frustrated from schoolwork and as well from the whole quarantine and social distancing that we're going through. This is now the beginning of week 5 of our social distancing, so that's pretty good in one way. The time is going by, but it's just crazy. It's been that long already. So with that said, let's begin with confidence intervals. So first, let's discuss some important ideas about confidence intervals. So first, this is the beginning of what we call the inferential branch of statistics. Everything we've done up to this point has been part of the descriptive branch of statistics, where we collect data, we graph it, we calculate averages and standard deviations, and kind of describe the shape of the data. Inference is now where we take what we've collected and we take what we've graphed and analyzed, and now we try to make conclusions from it. So to make an inference means to make a conclusion or a generalization based on previous information. So it's the branch of statistics concerned with using sample data to make generalizations about the big population. So these are some of the symbols that we have learned. We've learned most of them. Okay, we've learned the symbol for the mean. So remember, x bar is the sample average and mu is the population average. And then we have S and sigma for the standard deviations. When you square that, you get variance. And today we're going to be introducing a new variable, but it's nothing really new to you. It represents percentage. So P with a little cap on top, we'll call that P cap or P hat. That will be a percentage from our sample data, and then just regular P will represent the population percentage. So what we do, remember, in statistics is most of the time we collect sample data. So what we're really collecting is what you see here in the middle column that I'm circling. And we use these numbers to estimate these, right? Remember, there's a difference between them. The middle column, these come from sample data, small groups. And then these are the parameters that represent the big group. So we're not necessarily always guaranteed that these give us the exact answer for the population. Sometimes we have to estimate the population using these numbers. So we're using the symbols in the second column to help make estimates of the symbols in the third column. So how do we estimate a population parameter? How do we take a small group of 30 people and collect data about them to maybe make a conclusion or an inference about a group of 3,000 people or 3 million people? So the way we do that first is that we get what we call a point estimate. So a point estimate is just any statistical number. It could be an average, it could be a percentage. So it's a simple single number statistic, such as the symbols that you saw in the second column of that table. So then what we're going to do with that is we're going to construct an interval estimate, where instead of having a single number that estimates a big group, we're going to create a little bit of a margin or an interval of values that gives us a minimum and maximum range of what those values could possibly be for our entire population. So now, which is better? Is a point estimate, meaning a single number, is that the better estimate, or is the interval estimate better? The answer to that is interval estimate, because I'll tell you in the next slide, but it's going to allow for error, whereas a point estimate does not allow for error. So here's an example to illustrate why that is. So let's say, for example, and of course, This example here, you don't really hear much of down here, but remember, I'm from Philadelphia, Pennsylvania, so we always look forward to the snow forecast during the winter. So I always like to use snow as an example when I can. So let's say forecast A, they say tomorrow we're going to get 5 inches of snow. Versus forecast B, tomorrow we will get 2 to 6 inches of snow. So let's describe the two or compare the two forecasts. So first we can say that forecast A, it's a single number, so it's a point estimate. Forecast B, it's a range of numbers, so that's what we call an interval estimate. Which is better? Well, B is better, and here's why. If you're the forecaster on TV and you tell everybody we're going to get 5 inches of snow, if you're wrong, you're wrong. That could cost you your job if you make that mistake too many times. The better estimate, and this is what most statisticians and weather forecasters will do, is that they'll use interval estimates because there's a couple possible correct answers. 2 inches of snow, 3 inches, 4 inches, 5 inches, and up to 6 inches. So you could be wrong and right at the same time, which is better. So with forecast A, you don't have any room for error. With forecast B, there is room, which means you have a greater chance of being correct. Okay, so what are the components of confidence intervals? All right, there's some hidden numbers that you don't see in the interval itself. So when the forecaster tells you there's going to be 2 to 6 inches of snow tomorrow, there's some other information that goes into that you don't see. All you see is 2 and 6 inches of snow. So first off, the lower number, the 2, we call that our left endpoint or our lower boundary. So that's the 2 inches. And then the second number, the 6 inches, is the right or upper boundary. So we're going to call those L and R for the interval. Now, the interval has a center. So we're going to call that the mean of the interval. We're going to just call it M for now. So that's going to give us the center of the interval. Okay, and that center is going to be our point estimate. And also think about the center. So wherever your center is, it's also going to be equidistant to the left and right side of your interval, right? Just because you're finding the center, then you have the left and the right, which are equidistant to that center. So how do you find the center of two numbers? Just take their average. So you take the average of 2 and 6 inches. So 4 inches would be the center of that interval. And now we also have a margin of error. You've probably heard this term before, or at least seen it somewhere. The margin of error is just the distance from your center to the endpoints. So it gives the distance from your center M to either endpoint. And of course, those distances have to be equal because of that equidistance. Now, here's how you can find it. I mean, the numbers that we have here are simple enough. You can just do it in your head. But sometimes a little formula is more helpful when you have wacky numbers. So the margin of error is E. So how do you find distance between two numbers? You subtract them and take the absolute value so that it's positive distance. So you take the left endpoint and the center and subtract, or the right endpoint and the center and subtract. Take the absolute value and you get a positive value. So notice here, if you take the left, which is, remember, the 2 inches, and the middle is 4, that's the absolute value of -2 is 2. But also, if you do the right endpoint minus the center, that's also 2 inches. So that just means, okay, that we can also, in another way, state this interval, this 2 to 6 inch interval. We can also state that the amount of snow forecasted is 4 inches, which is the center, with a margin of error of plus or minus 2 inches, right? So you go 2 above 4, which is 6, and you go 2 below 4, which is 2, and that's how you can come up with the endpoints, just by taking your margin of error and adding and subtracting it to the center. So here are some formulas for the basics of confidence intervals. So these are the two that I just showed you. If you know the left and right endpoints, we can also calculate the middle value, or the point estimate of the interval, and also its margin of error. Now we can do that backwards. If we know the middle number and the margin of error, then to get the left endpoint, just subtract it from the middle, subtract the error, the margin of error from the middle, and add the error to the middle. And you can easily get your left and right endpoints for your prediction. So here's example 2. So let's suppose we have the interval from 4.1 to 11.3, and it's estimating some measurement, whatever it is. So what we want to do is use the interval there to find the values of L, R, M, and E. So L and R are given, right? Those are the left and right boundaries of the interval. So no work is needed for that. The mean, or the middle, is the mean of the interval. So just take the average and you get 7.7 would be the dead center of the interval. And how do you get the margin of error? Just subtract the mean and one of the endpoints. So there's 2 ways you could do it. The margin of error is the left endpoint minus the mean, or the right endpoint minus the mean. And then you take the absolute value and you get 3.6 either way. So the left and right endpoints are 4.1 and 11.3. The mean of the interval is 7.7, and the margin of error is 3.6. You could also say it's plus or minus 3.6. And also just notice again, if you do it backwards, where you take the mean minus the margin of error, the mean plus the margin of error, it gives you back the left and right endpoints. Example 3. So suppose that we know that the mean of an interval is 22, so that's our M, and the margin of error, or E, is 6.25. Calculate the interval. Well, so that's what we're given. M and E are 22 and 6.25. So to calculate the interval, we need the left and the right boundaries of the interval. So just by using the formulas I gave you, all right, the left boundary is M minus the margin of error. And the right boundary is M, the middle number, plus the margin of error. And then we get our interval, or the numbers that you see there after the equal signs. But it's better written like this. Just put them in parentheses, like it's like a little set of numbers. It's very nice. It's what we call interval notation. Okay, now with confidence intervals, remember there has to be room for error. So you're going to have to now specify a level of error for intervals. Now this is not to be confused with margin of error. So now we have 2 types of error that we're talking about here. So first we have the margin of error. Now we're going to be talking about the level of error. And the level of error is just the amount of error that we're going to allow in our measurement. In other words, the amount of error is our lack of confidence. So we're going to have a level of confidence, and we're going to have a level of lack of confidence. And they're going to be complements. So we're going to introduce a new symbol here called alpha. It looks like a lowercase a, and that's what it is in the Greek language. It's like a lowercase a, but in Greek it's called alpha. And remember, alpha means the beginning, so it's the first letter of their alphabet. Now, it's the variable that we use to denote the amount of error. And again, make a note that this is not the same thing as the margin of error. Now, also, sometimes the letter C is used to denote the level of confidence. That makes sense. And also note again, so remember, confidence and lack of confidence are complements. So when you add the 2 together, you're going to get 1 or 100%. So that means that C and alpha are percentages, and therefore they're also probabilities. So the probability of confidence is C. The probability of error is alpha. And here are commonly used values. And these are the ones you're going to see mostly. And I would strongly recommend that if I give you any tables of numbers, that you copy them down. So level of confidence, the most commonly used ones are 90, 95, and 99% confidence. And therefore, if you look at the errors, they're going to add each column up to 100. So if you have 90% confidence, you're going to allow for 10% error. If you have 95% confidence, you will allow for 5% error. And for 99% confidence, you allow for 1% error. So question is, why not use 100% confidence? Why not use 99%? Why use 90? Well, first of all, in statistics, you can't be 100% confident because the numbers that you're collecting from your data, they're going to serve as estimates for the entire population. So remember, an estimate always has error. You have to allow error. So there's no such thing as 100% confidence in statistics. Also, it's not always good to use 99% confidence. Bigger is not always better, and I'll illustrate an example later on why that is. Another thing we're going to want to do in this section is interpret a confidence interval. What does it mean? So now more specifically, yeah, we can identify the endpoints, but what do they mean? So in statistics, we'll usually describe a confidence interval with its level. We'll say it's a 95% confidence interval, or CI, and let's say it's for a population mean is between these two numbers. So here's how you can interpret this. So there's a very statistical way of interpreting it, and there's a very layman's term of interpretation. So here's the first interpretation. This is the statistical interpretation. So we would say that we are 95% confident that the true mean, meaning the mean of the population, is contained in the interval at alpha equals 0.05. So that's the statistical way. Here's another way you can state that, and it will make a little more sense. So we can say that we are 95% confident that the true mean is between 2.4 and 5.1, so that's the contained in the interval, with an error of 5%. Remember, alpha was the error, so when you say the error is 0.05, we mean we're allowing 5% error. Now, I'm going to introduce to you a new distribution, because it's needed. So number one, we talked a lot about this prior to your test 3. We talked about z-scores, the z-distribution, what we call the standard normal distribution. Okay, it's useful. All right, so now more specifically, when do we use it? Because now we're going to be using something else instead of z sometimes. So how do you know when you can use z? How do you know when you cannot use z? So first, z-distribution is useful when we know the population standard deviation sigma, or if n is really large, okay? So if you recall, a lot of the problems that we were doing, we kept using mu and sigma, all right? And that's because they satisfy the z-distribution. Now, if those do not exist, like if we do not know sigma, or if n is small, okay, then we use what's called the t-distribution for when sigma is unknown. So if sigma is unknown, what do we use in its place? Well, don't forget, we also have s, which comes from a sample. So we can use s as the replacement or the estimate for sigma, because you're not always going to know sigma. It's more realistic to not know your population parameters, because statistics are always trying to find those. So how can you know them from the get-go? The second point, just in case you see this in your homework or in the book, the t-distribution is sometimes called the student's t-distribution. And the reason why it's called the student's t-distribution is because when this was developed, it was developed by a mathematician by the name of William Gossett when he was working at the Guinness Beer Brewery plant in Dublin, Ireland. And he had noticed, because his samples of beer, he was working with very small samples. I guess you can only try so many before you get tipsy and you can't accurately measure what you're supposed to measure. So he was working with very small samples of like 5 or 10 or 15 items, I guess, that they were taste testing or measuring. And he noticed that with small samples, the variation is a lot more. So he realized that the z-distribution was not the most accurate way to come up with estimates of probabilities and other statistical values that you learned before test 3. Now, because he worked for Guinness, they would not allow him to put his name on the reports and the publications for the information regarding the beer. So because he couldn't use his name, he used a pseudonym. And he just called it student instead of William Gossett's t-distribution. So that was his pseudonym, and that's why it's called student. All right, so this point here is exactly what William Gossett discovered, that smaller data sets may have more variability, so the t-distribution will account for that. And also, the t-distribution is nearly the same as the z-distribution, but it's a little more wider. So, and that's because small data sets are a little more spread out. But now, as your data set size increases, the width will actually go back to what a z-distribution looks like. So t-distribution and t-scores, you're going to notice that they really work the same way as z-scores and bell curves. So just to kind of compare z and t a little more, so remember for x values, the z-score was x minus mu over sigma. Well, when you don't know sigma, then what you're going to have to do is replace it with your sample statistics. So therefore, instead of z, we would have t equals, now notice x stays in the same place, mu gets replaced by the sample mean x bar, sigma gets replaced by the sample standard deviation. So you notice it's really the same formula. The only difference is that over here we're using population parameters. Over here for the t-distribution, we're using sample statistics. And also remember, we learned a little bit about the distribution of x bar. Remember, x bar has a standard deviation of sigma over the square root of n. So if it's a t-distribution, sigma gets replaced by s, mu gets replaced by, nothing, it doesn't get replaced by anything. In fact, you need that for x bar. All right, so you have x bar minus mu and x bar minus mu. You can't change this to x bar because you'll always get 0, x bar minus x bar. All right, so mu doesn't change here, but it does up here. Okay, so that's one of the big differences between z and t that you need to know about. Okay, so now that's just information that I wanted to throw your way to teach you a little bit about confidence intervals. Now we're going to get really specific and start constructing confidence intervals for particular types of statistics. So this is the beginning of chapter 9 now, where we're going to look at a confidence interval for population percents, all right, percentages, like in a pie chart. We can do confidence intervals for pie chart values or other percentages, which we call proportions. So here are some symbols that you're going to need to know for proportions. So remember that p and p hat are percentages for a population and a sample statistic respectively. And because they're single numbers, all right, the number that we're actually going to have, right, well, number 1 is what we wish to know, so we don't have it. 2 is what we're going to get from our sample. So that's going to be our point estimate. It's a single number. The sample size here is going to be n, and in these examples, they're typically usually very large. So remember, in that case, if you have very large samples, you can use z-scores. And the z-score that we're going to use is what we call z sub alpha over 2, which is the z-score corresponding to the confidence level. And I'm going to explain a little more about that alpha over 2 in just a minute. But first, here's a table that you really should copy down and save it for your notes, because you're going to be using this table a lot, quite a bit. So the 3 confidence levels that I mentioned before, the 3 common levels, are at the top, and the z-scores that correspond to those are in the second row. You're going to need those z-scores. Now, what I would like to show you now is the meaning of z sub alpha over 2. So I'm going to use my iPad real quick. I'm going to reflect that. Wrong one. Okay, so I have my pad up now. So I'm going to talk to you about the meaning of this z sub alpha over 2. There we go. Z sub alpha over 2. What's the meaning of that? So let's take, for example, the 90% confidence interval, right, where you're told that z sub alpha over 2 is 1.645. Where is that coming from? So first, it's coming from our bell curve, where we have 90% of the data is contained between 2 particular values. And remember, because of symmetry, they're the same value but opposite in sign. One is positive, one is negative. So this is what a confidence interval looks like under a bell curve. It's literally just the amount of area between 2 particular symmetric values. So it's 90% of the area. So now, if this is our confidence level, if C is 90, what's alpha? Remember, alpha is the amount of error. So in this case, it's 10%, so that they add up to 100. Okay? Now, how much area is in the 2 tails of that curve, right? If you have 90% right there in the middle, then that means you have 10% remaining that gets divided up into both tails. So you have 10% over here divided by 2, and 10% over here divided by 2, gives you 5% in each tail. Now what's that 10%? That's the alpha. So you notice it's alpha divided by 2, And over here, it's alpha divided by 2. So when you say z sub alpha divided by 2, it's literally referring to the left-sided area in front of that negative z-score. Okay? So how would you find that using our calculator? So remember, you could do inverse norm with your calculator code, right? And you would type in the amount of area, which is 0.05, right, 5%, and then 0 and 1, because that's the mean and standard deviation of z-scores. And if you type that into your calculator, you're going to get 1.645 ... Okay? So that's the meaning of those particular numbers. Okay, so I'd like to go back to where we left off here. So the next step is to now look at how do we construct a confidence interval for a population proportion, right, which we're calling P. We're trying to estimate that, and it's given by the following quantities. So remember, we're going to need a lower bound and a right bound for the interval. So the point estimate is P hat, and then you're going to add and subtract the margin of error. And the margin of error is computed by the following. And this is something that you would learn in more of a statistical theory class. So you don't really necessarily have to know why the formula is set up this way, but just make sure you have it copied and you are using it appropriately. So the margin of error is the z-score that you take from the table multiplied by the square root of. So you take your point estimate p hat times 1 minus p hat, and you divide by n, and that will give you your margin of error. So now, that z sub alpha over 2, remember, is from the table on the previous slide. Okay, so this is one of the examples I have printed out for you on your NTS. Let's take a look at it. We're going to be skipping question B, by the way. All right, so we're going to skip question B. So a survey of 2,306 adult Americans aged 18 and older, conducted by Harris Interactive, found that 417 of the 2,306 have donated blood in the past 2 years. So what we'd like to do in question A is to obtain a point estimate for the proportion of adult Americans 18 and older who have donated blood in the past 2 years. So here's how you do it. So the point estimate is p hat, remember, and we're using that to estimate p. So p hat is from our sample. P is what we're trying to estimate in the whole population. So in our sample, 417 out of 2,306 have donated blood. And you have to set it up that way because we're trying to get a percentage from that. So when you divide that, you get 0.181. So a little more than 18% of our sample have donated blood in the last 2 years. So there's your point estimate. Remember, a point estimate is a single number, and that's what we got. So now we're going to use that to now answer C. Construct a 90% confidence interval for the population proportion. So this is going to help us estimate the proportion of all Americans 18 and older who have donated blood in the last 2 years. So first thing you need to note is that there's 2,306 people total. If you use the table on the last slide that I gave you, all right, that z sub alpha over 2 is 1.645 for 90% confidence. Okay, so make sure you look at 90% to get that value. I'm going to compute the margin of error first. So the margin of error is just by multiplying these quantities. So the z value is 1.645. P hat, we found that already, the point estimate, 0.181. And you subtract that from 1 and multiply those and divide by 2,306. So again, that's just coming from this formula on this slide here. So as long as you have the formulas, you can just plug in the numbers and bam. The margin of error is 0.013. And now we use that and we add that and subtract that from this point estimate. So the endpoints of the interval, so L and R, are just by subtracting and adding the error, the margin of error, to your p hat. So p hat was 0.181. We add and subtract the margin of error 0.013, and we get these values here. So therefore, the answer for C is the interval 0.168, 0.194. And then in D, we're asked to interpret this interval. Okay? So remember, this is like that statement I gave you in a previous example where you say that in this problem, we're 90% confident about something. So in this case, we're 90% confident that the true proportion or percent of adult Americans 18 and over who have donated blood in the past 2 years is between 16.8% and 19.4%. Also, make sure you're using your calculator to compute like our margin of error here. Make sure you're getting the same value as me. Just make sure you're not making any mistakes with that. All right, number 30. We have a survey of 700 community college students. 481 indicated that they have read a book for personal enjoyment during the school year. So A, we're going to construct a 90% confidence interval for the true proportion of all community college students who have read a book for personal enjoyment during the school year. So first, what are some things that we can pick out from this paragraph? So first, we can pick out our point estimate, p hat, which is just the sample percentage. So 481 out of 700 community college students, or 0.687, have read a book for personal enjoyment. Because the level of confidence is 90, our table will tell us that the z-score for this is 1.645. And therefore, the margin of error is that z-score times p hat, 1 minus p hat over n, all in the square root. And that comes out to 0.029. Again, make sure you try that on your own calculator. Make sure you can get the correct value. Okay, so next, let's get the endpoints. So the endpoint there, the left endpoint, remember, is p hat minus the margin of error, and then the right is adding the margin of error. All right, so these are your endpoints, and that's the interval there. Okay. Now for part B, we're going to do the same thing again, but this time we're going to change the level of confidence to 95. The objective here is to figure out what difference does it make if I use 90%, 95% confidence. What difference does it make? And that's what we're going to look at. And this is going to, again, go back to the point where I told you that bigger is not always better. Because we're going to be looking at question C now. We're going to compare answers A and B to look at the impact that it makes by changing the level of confidence. So for part B, for a level of confidence, the z-score from the table is 1.96. So now all we have to do is go back and update our margin of error. So the margin of error now only changes right here. Before we had 1.645, change that to 1.96. This stays the same, and now the margin of error is 0.034. So therefore, the endpoints will be our point estimate, 0.687, minus and plus the margin of error, and it gives you these values. So there's the 95% confidence interval. Now, what difference did it make by changing the confidence to 95? It doesn't necessarily make the answer better. Okay, so what you really might want to compare here are the margins of error. So for 90%, the margin of error was 0.029. For 95%, the margin of error is 0.034. And again, the margin of error you want to think of as like a distance. All right, so if that margin is bigger, that means the distance to the endpoints is bigger, which makes a wider interval. Okay, so 95% has a wider interval. So when you increase your confidence, you're making the interval wider and wider and wider. What's the problem with that is that it might just be too wide. It might contain so many values that no matter what you estimate, it's always going to be correct. And that could be wrong, right? The interval could be super wide. So let's say, for example, I have confidence on the next test that you're going to score between 0 and 100. What's your score going to be? You really can't estimate what you're going to get. It's too wide. But if I told you, you can estimate on your next test that your grade's going to be between 90 and 98. Now you know you're going to get an A, right? Now you can really narrow down what you can expect. So wider intervals aren't always good for estimation. Okay, so increasing confidence level widens the interval estimate. And again, you want to proceed with caution there that sometimes the intervals may become too wide for estimation. All right, so now I'm going to continue here with the last part of the lecture where we're going to be looking at constructing confidence intervals, this time not for percentages, but for population means or averages. Now, one thing I would like to first direct your attention to is that in the discussion room where you opened up this video, I also provided a link for you for a document called Table VII. And so Table VII is this document here with the t distribution. Make sure that you have downloaded that. I would also strongly recommend that you print it out. It's just so much easier to have a copy of it. If you have the actual textbook at home, this is in the back of your textbook, so you don't have to print it out if you have your own textbook. But make sure you have this. This is going to become very handy. All right, so continuing with confidence intervals for population means. Here are some symbols that we should be familiar with when we're talking about averages. So first, remember, mu is what we really want to know, the population mean. X bar is the estimate, or the point estimate that we're going to use for that from our sample. S is the sample standard deviation, because we're not going to know sigma. N is the sample size. And just like Z sub alpha over 2, we're going to be finding a T sub alpha over 2. Again, that's the t-score corresponding to the error level divided by 2. Remember, alpha is the error level, and when you divide it by 2, it's error divided by 2, because you have two tails. Okay? So now to get the t-score that we need, that Table 7 that I have provided for you will be very handy. And one other thing we need to remember is this thing called the degrees of freedom, which is, remember, n minus 1. So let's practice using Table 7. How do we use it? What do we need? So if you take a look at Table 7, what the goal is to find a number in the body of the table. And the number that we find is going to be dependent upon a row number and a column number. So we need two numbers to access the t-score that we need. We need a row number, and notice the row numbers are the degrees of freedom, and the column numbers are going to be the alpha over 2 values. The alpha over 2 values. So let me go back to that. So let's say, for number 1, let's say we had a sample size of 20 and an alpha of 0.10. What t value are we going to use for that problem? So first, we need to get our row number, which is the degree of freedom. So you have to do n minus 1, which is 19. The column number is the level of error alpha divided by 2. So in this case, it's 0.05. So now what I would do is I would go to the 19th row and the column with 0.05 at the top. So here's the 19th row, and 0.05 is up here. So if I can find the right spot, looks like 1.729 would be the value. There you go. So you would say T sub alpha over 2 is 1.729. Similarly, for n equals 15 and alpha equals 0.05, the degree of freedom is 14, and alpha over 2 is 0.05 divided by 2 is 0.025. So again, go to the row with a 14, the column with 0.025, and you should get 2.145. One other thing I want to point out about the t-distribution, remember that the t-distribution is better for smaller samples. But if your samples get larger and larger and larger, notice if you come down to the bottom of the table, if your samples get large enough, they eventually equal out to z-scores. All right? So when your samples are very large, your t-scores become z-scores. Okay, so now how do we get a population mean confidence interval, or a confidence interval, a CI, for the population mean? Well, just like for proportions, you have to do really two things. You have to get your lower bound and your right bound, which is your point estimate minus and plus the margin of error. And our point estimate, remember, for a mean is x bar, not p hat. So you also have to be attentive to the wording. When it says mean, the point estimate is x bar. And the margin of error is a little simpler here. It's your t value times the standard deviation s divided by the square root of n. So this one's a little nicer. So this example is also on your NTS, number 28. How much time do Americans spend eating or drinking? So suppose for a random sample of 1,001 Americans, 15 and older, The mean amount of time spent eating or drinking per day is 1.22 hours with a standard deviation of 0.65 hours. So we're going to be answering questions C and D only in this problem. So we're skipping A and B. So we want a 95% confidence interval, and we want to interpret it for the mean amount of time that all Americans 15 or older spend eating and drinking during the day. So first we know that there are 1,001 people in my sample. We know that the sample average x bar is 1.22 and standard deviation is S. So that's an S because it's from a sample, which means sigma is unknown, which means use the t-scores, not the z-scores. So now, what t-score do I use for this? Well, this one is at the very bottom of the table, second row from the bottom, right? The degree of freedom is 1 from 1,001, so 1,000, and alpha over 2 is 0.05 over 2. Now, it doesn't tell you in the problem that alpha is 0.05, but I can get that from the confidence level. If my confidence is 95, then my error, alpha, is 5%. So it's 5% divided by 2 is 0.025, or 2.5%. So that's remember my row and column in the table, right? My row and column in the table to get the t-score 1.962. All right, now using the margin of error formula, take the t-score, multiply it by S divided by the square root of n, so it looks like this, and you get 0.04. So now, to answer question C, the left and right boundaries are the sample mean, which is our point estimate, minus and plus that margin of error, which gives you 1.18 and 1.26. So that's your confidence interval. You're also asked to interpret this. So this is one of those statements where you say, we are 95% confident that the mean amount of time Americans age 15 or older spend eating and drinking per day, it's very wordy, is between 1.18 and 1.26 hours. So a conclusion like this, I really want you to specify the context. So it's wordy, but I would like you to write it, okay? It will keep you mentally healthy. All right, now D. So here's the answer. So D asks, could the interval be used to estimate the mean amount of time a 9-year-old American spends eating and drinking each day? The answer is absolutely not, because the collected data that we have represents only those Americans that are 15 and older. So a 9-year-old is not represented by this data. And now our final example, crawling babies. So we have a sample of 12 mothers here, which they were asked the age in weeks at which babies first crawled. So we have 12 different babies' times in weeks when they first crawled. So we want to construct and interpret a 95% confidence interval for the mean age at which a baby crawls. All right, so how are we going to do this? What we're going to have to do is we're going to have to plug these numbers into our calculator to get some statistics, because the only thing that's given are 12 numbers. And we're going to need our sample average, which is our point estimate. We need the standard deviation. We already know that n is 12, right? We know n is 12. We know that the confidence level is 95. Therefore, my alpha error level is 5%. So what you would have to do is hit stat, go to number 1, edit, type in your numbers, all right, and then stat, calc, 1var stat, and then list 1. So right there, there's your statistics. All right, x bar is 38.25. S is about 10, so I'm just going to write 10, and we know n is 12. So then the next thing you have to do is get your t-score from the table, Table 7. So remember that the row is n minus 1, so 12 minus 1 is 11. Alpha was 5%. You're dividing that by 2, which gives you 0.025 for the column number. All right, so therefore 2.201 is the t-score. So now the margin of error is the t-score times s divided by the square root of n. And that gives you 6.35, which now we can get our endpoints for the interval. We can construct the interval with this much information. So the left point is the mean minus the error. The right endpoint is the mean plus the error, and that gives us these two numbers here. And that's our interval. So now we also have to interpret the interval. So we would say that we're 95% confident that the mean age at which a baby first crawls is between 31.9 and 44.6 weeks. That's a very good answer if you write it that way. Okay. So that is the end of the lecture. Remember, your NTS is due by 5 p.m. today. I will post a homework on Thursday after your second lecture. And there'll probably also be another lab. So you all have a good day. I hope everybody is doing well and healthy. Take care. Bye.